Hi everyone, welcome back to this channel. Imagine you open TikTok and instantly videos start playing smoothly, one after another. You like a few, comment on one, and even upload your own video, all within seconds. But behind this lightning fast experience, there is a massive engineering challenge. So today, let's try to design TikTok from scratch and see what it actually takes to make this magic happen. In this video, we are going to walk through the core system design behind TikTok, focusing on the key components that make video upload, playback, and interactions work at scale. We will look at how videos are uploaded and streamed, how user feeds are generated, how likes and comments are handled, and how we keep everything low latency and reliable, even when millions of users are online at the same time. Before diving into the architecture, let's set the stage by defining what features our TikTok-like app needs to support and what system qualities we are aiming for. So core functional requirements. Let's start with this one first. These are the features users actually interact with. First, upload videos. Users should be able to record and upload short videos. Second, display video feed. Users should be able to scroll through videos seamlessly, one after another, with almost zero buffering. Third, user interactions. Users can like, comment, and share videos. These interactions should feel instant, even if the system is updating data in the background. Now, let's talk about non-functional requirement. The system-level goals that makes TikTok too smooth and reliable. First, low bandwidth uploads. Since most users are on mobile, we need to optimize uploads. Second, low latency feed. When users scroll, videos should start instantly. Third, scalability. Our design should handle billions of uploads and concurrent viewers. Fourth, durability. Once a video is uploaded, it must never be lost. Now, these are the main core features. Other than this, TikTok has many other features, but we are not going to discuss in this video. Some of the features which are out of scope is recognition algorithm. Second, live streaming. And last, advanced analytics and content moderation. There are a few more which is basically like user profile, etc. But we will focus on main requirements only. These are the foundations of our TikTok system. Next, we will see how all these pieces connect, from the upload service to CDN delivery, and how we make this system both fast and reliable. Now, let's start with high-level design. In high-level design, we are going to focus on main core features and core functionality of the system. And basically, we will just focus on what are the core components to be used in high-level design. We will start with our first requirement, which is upload videos. So basically, video is being uploaded into TikTok by client or our select user. So when user logs in into the TikTok and they try to upload the video, the request will go from client to API gateway. And API gateway will help route this request to API server. Apart from simply routing requests, an API gateway also provides several powerful features, things like rate limiting, authentication and authorization, load balancing, caching, request or response transformations, and centralized monitoring and logging. These features help improve performance, security, and reliability across your entire API ecosystem. Now, once we get all the requests in Upload API server will create an entry into the database. And the entry will be just for the metadata, which will include some basic information related to video, which is like video ID, video title, etc., or created date, etc. And at the same time, once the entry is created in database, Upload API will send a request to S3 to get presigned URLs. So why do we need presigned URLs? We can just directly upload raw video in S3, right? But the reason is basically if a user, a client is trying to upload a very large video, and if we try to upload a very large video directly in S3, then there will be a bandwidth issue. Plus, another thing is if there is a network issue, I think things might break. Second, if it's just a large video or a large raw video we are storing, so at the time of streaming, it will be hard to stream faster. So instead of doing just large raw video into S3, we will send request to S3 to get presigned URLs. Once Upload API gets the presigned URLs, it will send all presigned URLs back to the client, and then client will upload video in small chunks to S3. By doing this, we will save a lot of bandwidth. We will not even use API gateway or anything in this case. So in this case, the request goes directly from client to S3, and it will have a great bandwidth savage here. Now, once all the chunks are uploaded into S3, client will mark as complete, and then in that case, S3 commits multi-part upload. S3 will start enqueue all these chunk URLs into Kafka or SQS for transcoding. Now, why do we need transcoding here? So the thing is, we need to support multiple devices. When TikTok is being used, people might be using TikTok via cell phone or via our desktop, etc. So in that case, each device has its own different transcoding. So we will send requests from S3 to Kafka or SQS for transcoding. Once requests are in SQS, we will transcoding server, or I would say like transcoding workers, will start getting this request from SQS. It will start processing and start converting into different resolution. Once it converts and completes resolution for all the chunk URLs, it will upload all the transcoded URLs into S3. And once transcoding completes and once all the URLs are saved into S3, transcoding workers will also mark the status as complete for this particular URL into database with the playback URL for this transcoded video. So this is how our upload video process works. Now let's look into our second feature, which is display video feed. In this case, what happens is when client requests to get the feed, the request will go from client to API gateway, and client API gateway will basically route the request to feed API. Feed API will check data first into Redis cache. Basically, it is just trying to find out metadata related this feed in the cache. And for any reason, if we have cache miss, which is basically like if we didn't find data into cache, in that case, feed API will send question or query to database directly. It will get all metadata related data from DB, and once it gets all the metadata, then it will send response back to the client, and client will stream video directly from CDN. So by using CDN, basically like we will have low latency in terms of displaying or streaming video. So this is how our upload. This is how our video feed. This is how our display video feed feature work. Now let's look into our third feature, which is user interaction. Basically, on video, user can click on like, comment, or share feature. So when user does that, the request will go from client to API gateway, and then client API gateway will send a request to interaction API. Once interaction API gets the request, we will send this request related to like, share, or comment to Kafka or SQS. Basically, for this kind of feature, it's okay to have eventual consistency, because if we display like number of likes instead of 3, if we display 1, it's okay. We are not losing out on any particular critical transactions. But we also want to make sure that we don't lose any of these likes or related data, likes or compensatory data. And that's why we will send request to Kafka or SQS. And then from here, from this queue, all the requests related to interactions will be updated into the database. So this is how our interaction flow will work. Now, let's take a deep dive into one of the most critical parts of a video platform like TikTok, the chunk upload workflow and Presigned URLs. This is what allows users to upload large videos quickly, reliably, and efficiently, even over mobile networks. Imagine you are trying to upload a 200 MB video from your phone. If we try to send the entire file in a single request through our backend servers, a small network hiccup could fail the whole upload, and you would have to start all over. That's frustrating and inefficient, especially when millions of users are uploading videos simultaneously. To solve this, TikTok and similar platforms break videos into smaller chunks, usually 5 to 10 megabytes each. This process is called chunk uploading. Think of it like sending a large parcel in smaller packages. If one package gets lost, you only resend that piece, rather than the entire parcel. This makes uploads resumable and robust against network failures. But there is another challenge. Our video files are stored in Amazon S3, which is private. Only servers with AWS credentials can upload directly. We don't want to give AWS keys to every client device because that would be a huge security risk. This is where Presigned URLs comes in. A Presigned URL is essentially a temporary secure link that lets your browser upload a chunk directly to S3 without going through our servers or exposing sensitive credentials. Here is how it works. First, the client requests an upload session from an upload API by sending basic metadata like the video title, description, and file size. The upload API creates an entry into metadata database with the status in progress and then initiates a multi-part upload in S3. The API generates the first Presigned URL for the first chunk and returns to the client. The client then uploads that chunk directly to S3 using this Presigned URL. Notice that the actual video data never passes through our backend servers. This offloads bandwidth, reduces server load, and allows thousands of users to upload large videos in parallel without overwhelming the system. Once the first chunk is uploaded, the client requests Presigned URL to subsequent chunks and repeats the process until all chunks are uploaded. During this process, the upload API can optimally track progress in the database or in a cache like Redis. This enables resumable uploads. If a network failure occurs, the client can detect only the chunks that failed rather than starting the entire upload over. Once all chunks are uploaded, the client calls a complete endpoint. The backend then finances the multi-part upload in S3, merging all the chunks into a single object. At this point, the system enqueues a message into a queue like Kafka or SQS to trigger the transcoding workflow. A transcoding worker picks up the message, downloads the raw video from S3, generates multiple resolutions, for example 480p, 720p, etc., and splits them into HLS or dash segments. These transcoded files are uploaded back to S3. Finally, the worker updates the metadata database with the final status, playback manifest, resolutions, bitrates, duration, and thumbnail information. Later, when the client fetches the feed, it will receive this metadata including the playback URLs and will stream video segments directly from the CDN. The CDN pulls content from S3 on demand and caches it at edge locations, ensuring low latency and smooth playbacks for viewers around the world. In summary, chunk uploads with Presigned URLs allow us to handle massive concurrent video upload efficiently, securely, and reliably, while keeping backend servers free from heavy bandwidth usage. This workflow is the backbone of a scalable video platform like TikTok, enabling millions of users to upload videos seamlessly every day. Now that we have seen how chunk uploads and Presigned URLs allow users to upload videos efficiently, let's shift our focus on the other side of the pipeline. How those videos are stored and delivered to millions of viewers around the world with low latency and minimal bandwidth usage. And those are our non-functional requirements which we are going to focus on now. So, once a video is transcoded into multiple resolutions, all the transcoded files including HLS or dash segments and playlists are stored in Amazon S3. S3 acts as our durable, highly available object store, capable of handling millions of video files and concurrent requests without worrying about data loss. Think of it as our backbone storage for all video content. But storing videos in S3 is only half the story. If every user had to fetch video segments directly from S3, latency would be very high, playbacks might stutter, and the backend would face massive bandwidth cost. This is where a CDN or content delivery network comes in. The CDN caches video segments and playlists at edge nodes around the world. When a client requests a video, it fetches the data from the nearest CDN edge, dramatically reducing latency and improving throughput. Essentially, the CDN acts as a high-speed global video delivery layer. To ensure smooth playbacks on any network, videos are transcoded into multiple resolutions, and the client dynamically selects the segment quality that matches its current bandwidth. This approach optimizes bandwidth usage and combined with CDN caching allows the system to scale to millions of viewers efficiently. From a system design perspective, the flow looks like this. The transcoding workers upload all the processed video segment and playlist to S3. The metadata database stored in the playback path, resolutions, and bitrates. When a client requests a video from the feed, the API returns metadata including the CDN playback URLs. The client then streams the video segments directly from the CDN, fetching each segment in sequence based on the adaptive manifest. The CDN automatically caches segments at edge nodes, so subsequent viewers nearby experience even faster playback. In summary, by combining S3 for durable storage, a CDN for low latency global delivery, and adaptive streaming to optimize for bandwidth and device capabilities, we ensure that users can watch videos instantly and smoothly. So no matter where they are or how fast their connection is, this addresses two of our most critical non-functional requirements, low latency and low bandwidth, and makes Chipsoft's massive platform more truly scalable and performant. Now that we have seen how videos are uploaded, stored, and delivered efficiently, let's talk about a major real-world challenge. And this challenge is basically, like many times, a very popular question being asked during interview: the hot celebrity or viral video platform. Imagine a video from a celebrity suddenly going viral. Millions of users try to view it at the same time. Without proper handling, this can overwhelm the backend database and storage, leading to high latency or even downtime. To handle this, we rely heavily on caching or CDNs. Popular videos are cached at edge nodes globally, so requests are served directly from CDN rather than hitting the origin S3 or the backend APIs. This drastically reduces load on servers and ensures low latency playback, even during traffic spikes. In addition, we cache metadata such as likes, comments, and views count in fast in-memory stores like Redis. This allows the feed APIs to respond quickly without querying the database for every single request. However, updating metadata like likes or view count for a viral video can also become a bottleneck. Writing every user interaction directly to the database will overwhelm it. Instead, we use asynchronous updates. The client writes interactions to a write-optimized queue such as Kafka or SQS. Worker processes consume these messages and periodically update the database and caches. This approach ensures image. By combining CDN caching, metadata caching, and asynchronous updates, the system can scale to millions of concurrent viewers without degrading performance. Even if a video suddenly becomes viral, most requests never touch the backend directly. They are served from the edge. The backend only handles essential processing like updating the database in batches and managing less frequently accessed videos. In essence, this strategy addresses two critical non-functional requirements: scalability and availability. The CVN ensures that video delivery remains low latency under extreme traffic, while asynchronous metadata updates and caching prevent database overload. Together, this technique allows platforms like TikTok to serve viral content reliability even during traffic spikes that would crash most traditional systems. Finally, let's talk about another critical aspect of building a large-scale video platform: monitoring durability and observability. Even if your upload, storage, CDN, and streaming systems are designed perfectly, without proper monitoring, you won't know when something goes wrong, and small issues can quickly snowball into major outages. First, durability. All video content is stored in S3, which provides 11 nines of durability. This ensures that even if individual nodes fails, your video are never lost. For metadata, databases like Cassandra or Postgres can be configured with replication to survive server or data center failures. Periodic backups and application across region further guarantees that both video content and metadata remain safe. Next is monitoring and observability. In a system like TikTok, millions of requests are happening every second. We need to track system health in real time. Metrics like upload latency, transcoding queue length, CDN hit ratios, cache misses, error rates, and database response times are collected and monitored using tools like Grafana or HuGet. Distributed tracing allows us to track a request end-to-end, from the client's upload or feed request to the CDN delivery, helping us pinpoint bottlenecks of failure quickly. Alerts and dashboards play a critical role. If a transcoding queue grows too long or if the CDN cache miss rate spikes, the operations team can react immediately. Combined with auto-scaling, health checks, and retires, this ensures that the platform remains highly available even under unexpected traffic surges or component failures. Ultimately, monitoring and durability gives us reliability and observability. They allow engineers to ensure that videos are safe, uploaded completely successfully, and users always experience smooth playback. Without this layer, the system would be opaque and fragile, unable to meet the high expectation of millions of daily users. To summarize, today we walked through the system design of TikTok from end to end. We started with the core functional requirements: uploading videos, batching video feeds, and enabling likes, comments, and shares. We discussed non-functional requirements like low latency, low bandwidth, scalability, and durability. We then took a deep dive into the chunked upload workflow and Presigned URLs, showing how videos are uploaded efficiently and securely. We explored video storage in S3, serial delivery, and adaptive streaming, explaining how content is delivered with low latency and optimized bandwidth usage. We also covered the Observability or viral video platform, and how caching's asynchronous updates help the system scale during traffic spikes. Finally, we touched on monitoring, durability, and observability, ensuring the platform remains reliable and highly available. By combining these design principles, scalable storage, efficient delivery, caching strategy, asynchronous updates, and robust monitoring, TikTok can deliver millions of videos smoothly to millions of users simultaneously while keeping the system reliable, performant, and cost-efficient. That wraps up our deep dive into designing TikTok. I hope this gives you a clear understanding of the engineering challenge and solutions behind one of the most popular video platforms in the world. If you enjoyed this video, don't forget to like, share, and subscribe for more system design deep dives.